Last time we law, and we saw how we can add reactions together algebraically. And through that, we can find out the enthalpy of the reaction. Now this is useful because it allows us to figure the enthalpy involved in a reaction without having to directly measure that process. Now, if we standardize this idea, we can get an even more useful idea. So we have to define the standard state, and so under these conditions we can have an enthalpy that's standardized. Now we're going to deal with this enthalpy of formation. So this is the enthalpy associated with the formation of a substance from its elements. It's important to note a few things in that regard. A diatomic element like 2 or oxygen, the elemental form is defined as the diatomic form, since that's the lowest energy. And if we have carbon, for instance, where carbon could be both graphite or diamond, graphite is the lower energy form and is therefore the elemental form. So the standard enthalpy of formation values have been found for many compounds, and using this data we can figure out the standard enthalpy changes. So let's take a look at some examples. For instance, here we can see enthalpy of formation for a number of different compounds. So it's noteworthy any element enthalpy of formation is 0, it's already there. There's no formation take place. Let's see how we can use this. We write the equation for the formation of calcium carbonate from its elements and identify the standard enthalpy of formation for calcium carbonate. So we want to write the equation that shows how calcium carbonate is formed. So this is calcium carbonate. So if that's our product, let's think about what elements would be necessary to produce this product. Well, we can see that we have calcium, and we have carbon, and we have oxygen. So those are the elements involved in producing this product. We have calcium plus the carbon plus oxygen. Now, for oxygen, the standard state is O2. So that's the elemental form of oxygen since it's diatomic. And note also that for carbon, carbon is diatomic, or I'm sorry, carbon is the elemental form would be graphite, the lowest energy form, as opposed to diamond. Put the state of matter in these. So we have calcium plus carbon, and oxygen makes calcium carbonate. Now this reaction will need to be balanced. So we need to adjust for the oxygens. All right, now when we look up on the table the enthalpy of formation for calcium carbonate, that enthalpy, so for calcium carbonate, might be a little hard to see there, so it's 1, -1, 1,207.6. Now notice the unit, kilojoules per mole of the calcium carbonate. Since it's kilojoules per mole, we'll need to adjust our equation here. If we put that number and associate it with this equation, notice that we have 2 moles of the calcium carbonate. So we'll need to reduce the ratios of this equation. Everything needs to be divided in half. So we're going to divide that in half, this in half, everything divided in half, so that we have 1 mole of calcium carbonate as the product. So that would give us Ca plus C in the form of graphite plus 3/2 oxygens makes CaCO3, and we can report then that the standard enthalpy of formation is negative 1,207.6 kilojoules per mole. And this little symbol here looks like a degree sign, is just a way of showing that it's the standard enthalpy of formation. Let's look at another example. Let's say that we have this equation, and now we're going to find the enthalpy for the reaction. So if we wanted to do that, we could look at the enthalpies of formation for each of these. Let's take a look at how it works. So, for instance, we could look at the formation of this reaction, of this compound, C3H8. We could look at the formation of O2. We could look at or O2 is already an element, so we wouldn't need to do the formation for that. The formation of CO2 and the formation of H2O. Let's write each of those down. So for instance, for C3H8, its formation is we would have carbon and hydrogen, we would need to balance that equation. So this would be for the C3H8. For CO2, we have the carbon, once again, in the form of graphite, and oxygen, and lastly, then for the H2O, we have hydrogen and oxygen. So the formation of each of these has a value that's associated with it. And so the standard enthalpy of formation can be looked up for each of those. And we'll find then that for C3H8, for 1 mole of C3H8, that's 103.85 kilojoules. Then for the next one, CO2, that's 393, negative 393.5 kilojoules. And then last, for H2O, that's negative 285.8 kilojoules. Now this reaction, like the last one, we should have that in order for it to appropriately match the number here. So this would actually be 1 H2O, and this would be 1/2 O2, and 1 H2. So if we can use Hess law here, then we can figure out the overall enthalpy change for the reaction. So just like we saw with Hess's law, we can move our flip the equations and do a little work with this and figure out the overall enthalpy change for the reaction. So since this is a reactant, the C3H8, let's flip that over to the reactants. Let's flip this reaction around. So in that case, we have C3H8 makes 3 carbons, 4 hydrogens, and the enthalpy of formation, we have to change the sign on that. So now it's negative 103.85 kilojoules. The other ones can remain in the same way they are, since CO2 is a product and H2O is a product. So we have C plus O2 makes CO2, and that enthalpy of formation is negative 393.5 kilojoules, and we have H2 plus 1/2 O2 makes H2O, and that enthalpy is negative 285.8 kilojoules. So let's balance this equation, cross out anything that's on both the left and the right, as we did before with Hess's law. So we have 3 C's here. We're going to need to get those 3 carbons. So we need to get the carbons to match up. We'll need to multiply those coefficients by 3. 3 there. That means this will also be times 3. We have, in this case, the hydrogens, 4 right there. We'll need 4 here. And so that's going to give us 2 and 4. So drop out anything that crosses out. This would be times 4 as well. Hydrogens cross out. And so the carbon also crosses out. And we have, for our equation, the original equation, C3H8 plus 5 O2, 3 and 2 makes 5, makes 3 CO2 and 4 H2O. And we can add up the enthalpies now for the reaction. And when we do that, we end up with negative 2,220 kilojoules. So the purpose of this is to notice a shortcut. So let's see something interesting here. Now, if we were to add up the total amount of the total enthalpy of formation of the products and subtract that from the total enthalpy of the reactants, let's see what we would get. So the products added together, so that would be the 103.8 kilojoules here. And if we subtract from that the enthalpy of the reactant, notice that we end up with a formula that looks like this. So the N stands for the number of moles of the products, or the M is the number of moles of the products, and the enthalpy of the products minus the enthalpy of formation of the reactants will equate to the total enthalpy of the reaction. So the N here for each one, let's take a look at how that would work. So if we, in this equation, multiplied the N value for each reaction of the products, so 3 times the enthalpy of formation of CO2, and so that is given to us right there. So 393.5 kilojoules plus the enthalpy of formation of the other product, so that'd be water. So that's going to be the coefficient for water then on this equation is times negative 285.8 kilojoules. And then we subtract the coefficient for the enthalpy of formation of C3H8, so that would be 1 times its formation, which is up here. Now we're using the positive value though for the enthalpy of the original formation of that, 103.5 kilojoules. And then also the oxygen's enthalpy formation is just 0, minus 0. Notice that by doing this equation, subtracting the sum of the formations of the products from the reactants, exact same thing that we did up here. Notice the way the coefficients match. See that 3 matches this here, matches this 4. And then the negative sign on this matches the subtraction negative sign. Since we flipped that reaction around, it becomes a negative from the equation. So a much simpler way to problem, we simply just plug it into this formula, and so that comes out the same answer. So we can use this formula, the sum of the enthalpies of formation of the products minus the sum of the enthalpies of formation of the reactants equals the enthalpy of the reaction overall. There's some algebraic manipulation we could do for this as well. Perhaps we might be given a problem where we're asked to find one of the products given the enthalpy overall of the reaction. And so we just use algebra and we plug in the value we have here and solve for an unknown.